Hey, how's everyone doing? It's me again.
Yesterday I started thinking, what could be interesting enough to be the subject of the next video? And it suddenly hit me. Magnets.
And the reason why I consider them an interesting topic was because we all know about magnets, right? They're that metal that attracts other metal, right? Simple, right?
Wrong. Well, maybe not wrong, but it isn't the full picture of what exactly is the physical phenomena of magnetism, or electromagnetism for that matter. There's several forms of magnetism, so let's start with a quick overview about the most common ones. The ones we know the most, the metallic kind. Like I mentioned before, I'm sure you're all aware of the everyday magnet, but how exactly does it function? Some of you may be aware that magnets have two poles, the north and the south. So if you try and connect two different magnets by their north poles, you will see that they repel each other. Similar if you try to connect them by their south pole. This will continue until you invert one of the magnets, meaning opposites attract.
So before we get too deep into what magnets are, I'd have to address some basic information that we're going to need to understand it.
You see, as established in the previous video about colors, the electrons in an atom move around in their own wave, and they can basically be spinning in one direction or another. This is what we refer to as the quantum spin.
Basically, electrons inhabit orbitals, and only two electrons can fit in each orbital.
Some fancier elements with bigger number of electrons break into suborbitals to fit them all.
Or more than one simple orbital.
These electrons can be positioned either pointing upward or downward. It's strictly binary, hence the positive and negative signs. And the half is to indicate that only two electrons can be fitted within a single orbital.
Have I lost you yet? Don't worry too much about this. There's an easier example.
Imagine a bus with empty seats, and as people start entering, they begin seating themselves on a bench. The first person to get on the bus has free range as where to sit, and every person likes to have a whole bench for themselves, if possible, and not too overcrowded. Electrons do the same with orbitals. They first select an empty orbital to have as much free space as possible, and will come back to fill the remaining space on an occupied orbital if all empty orbitals have been taken. So just like humans, electrons really like their space. With electron movement comes an electromagnetic field. The more electrons that are unpaired in their orbital and have the same orientation, the more electromagnetic forces will amplify each other. This is what makes a material paramagnetic. And the opposite is also true. If you have a positive half and a negative half electron spin within a single orbital, the electromagnetic forces will cancel themselves out to zero.
These types of materials are known as diamagnetic, and they basically make up all the matter which we consider non-magnetic.
Okay, so getting back to paramagnetic materials, the poles of each magnetic atom are not oriented. They have different direction in poles, and so this tends to negate the magnetic properties at a macro level. This also happens with diamagnetic materials, but seeing how they are not magnetic at a nuclear level to begin with, their orientation is irrelevant at a macro level. But what happens when we force them to align? And how do we do that? Well,
with an electromagnetic field, of course.
What we see is that paramagnetic materials behave like small little magnets, connecting their south poles with the field's north pole. Or, in other terms, it aligned itself in the same direction as the field. Whereas diamagnetic materials repel themselves from the field. You could have easily assumed that they wouldn't interact at all, seeing how they don't possess a polar nucleus or molecule to begin with. And this is true, but other physical phenomena happen when a force field is applied. Phenomena that I'm not going to get into here, for the sake of simplifying an already complicated subject. Fun interesting bonus fact. With all the previous information said, we can predict that even the non-magnetic materials can still be moved by magnetic fields that are strong enough, which was the case for a certain diamagnetic frog, which some scientists made levitate by placing it in a chamber with a strong electromagnetic field.
It's time to stop!
We ourselves could be repelled just like that little frog. The only difference is that we're significantly bigger and heavier. So a field that's stronger would have to be used to push us away. But in theory, we can be moved around like a magnet.
And a similar phenomenon happens with paramagnetic objects. The only difference is that instead of being repelled by the electromagnetic field, it's actually attracted towards it.
Now that's all fine and well, but I still haven't tackled the issue of the everyday magnet, which is a metal-based magnet. How do they work?
These magnets are called ferromagnetics. These types of materials behave very similar to the paramagnetic ones, with a clear difference. They form magnetic domains, where on the paramagnetic materials, the magnetic atoms are disoriented. In ferromagnetic ones, they form little pockets of oriented poles, and they can be fully oriented if placed under a magnetic field, be it by another magnet or an electromagnetic field. Now there's two types of ferromagnetics. We call them soft and hard. The soft ferromagnetics are called this because once you remove the electromagnetic field, the metal goes back to the way it was before it, so it disorients its orientation. And the hard ferromagnetics are metals that once they orient themselves to a field, they tend to keep that orientation. So these are the everyday magnets which we use. Final bonus fun fact. The Earth is a giant magnet.
It's more like an electromagnet, but still.
Due to its core being molten materials which are in constant movement inside of it, making our Earth have a north and a south pole. This is fundamental for life on Earth as we know it, because it protects us from cosmic radiation and other charged particles. Not to mention, it's the reason why compasses work and we can see the aurora borealis.
So what do you guys think about this? Because I personally am blown away how something as small as an atom and the electrons within it can have such a macro scale effect, like in our planet, for example, and how this effect is quintessential for life as we know it to thrive in this planet. I think that's mind-blowing to say the least, and it's one of the reasons why I love physics. So that's all for today. Thank you so much for sticking till the end, and hopefully now you do know how magnets work, or at least slightly more so than when you came into the video. This was Rick, and I'll see you in the next one.
Hey guys, thank you for sticking till the end. Did you enjoy this one? If you did, please hit that like and subscribe button. I will try and make at least one video a week, but depending on how long or complicated the subject is, I might take a little bit longer. Hopefully I'll see you in the next one. See ya.